In this video, we will go through scientific notation, the metric system, and significant digits. With scientific notation, this may be review for a lot of you. For some of you, it may be a little fuzzy in your brains. For some of you, it may be new material, but we'll take some time to go through it nonetheless and refresh ourselves about how to properly express numbers in scientific notation. So scientific notation, why do we use it? Well, it's often used to express either very large or very small numbers, and it is based on the use of exponents. In scientific notation, a number has the form of x times 10 to the exponent n, where x is a number that is greater than or equal to 1, but is less than 10. And 10 to the n is a power of 10. So when we write a number in scientific notation, this number here, x, has to be greater than or equal to 1, but less than 10. So for example, if we had 1 times 10 to the 2, this would be considered proper scientific notation. So this would be okay. If we had something like 9.999 times 10 to the 6, this would also be considered proper scientific notation because the number here is less than 10. So that would be proper scientific notation as well. Improper scientific notation would be if we had something like 0.9 times 10 to the 3. This would be improper scientific notation, as the 0.9 here is a number that is less than 1. So this would be incorrect. It would also be incorrect to write something like 10.1 times 10 to the 5, for example. The number 10.1 is greater than 10, and we want a number that is less than 10. So this would also be considered incorrect scientific notation. When we're dealing with large numbers, to express a large number in scientific notation, the decimal at the end of the number is going to be moved to the left. The exponent of 10 will end up being a positive number, and the number of places that you move the decimal point is the number in the exponent. So let's take a look at an example of how this works. So Mercury is about 58 million kilometers from the sun, whereas to write 58 million in scientific notation. So taking that number, 58 million, converting that into scientific notation, we'd have to pretend that we have a decimal at the end of that number. And we would move that decimal, we'd keep moving that decimal until we had that number that was equal to or greater than 1, but less than 10. So in this case, we have to place the decimal in between the 5 and the 8. So that number that we start off with is going to be 5.8. We don't write the zeros afterwards. And we'll discuss when we write zeros and when we don't write zeros later on. But for now, we don't write those zeros. So we have 5.8 times 10 to the power of an exponent. And to figure out what that exponent is, we count the number of places that we move the decimal. In this case, we moved it 1, 2, 3, 4, 5, 6, 7 places. So this is going to be our exponent now. So we have 5.8 times 10 to the 7. With small numbers, to express small numbers in scientific notation, the decimal point at the front of the number is going to be moved to the right. Because it's being moved to the right, the exponent of 10 will be a negative number. The number of places that you move the decimal is the number in the exponent. So in the following example, we're told that an electron in a hydrogen atom is a very, very, very small distance from the nucleus, rather large on that atomic scale, but very small from our perspective. So we're told to write this very small number in scientific notation. So similar to the previous example that we just went through, we take the decimal place, and in this case, the decimal place is provided for us. We don't have to imagine that it's there. And we take this decimal and we move it to the right until we get that number that is greater than 1 or equal to 1, but less than 10. So in this case, our decimal is going to be placed between the 5 and the 3, and so that is going to be the number at the beginning of our scientific notation. And of course, it's going to be multiplied by 10 raised to a certain exponent. To figure out what that exponent is, we simply count the number of decimal places that we've, the number of places that we moved our decimal. So in this case, we would have moved it 10 places to place it between the 5 and the 3. Because we've moved it to the right, that exponent is going to be a negative, and since we did move it 10 places, our exponent is going to be a 10. So taking that small number and writing it in scientific notation, we get 5.3 times 10 to the negative 10. Now, sometimes you'll be asked to convert from scientific notation back into standard notation. The number with the zeros, all those zeros at the end, or all those zeros at the beginning. So when you convert from scientific notation to standard notation, the exponent of base 10 will tell you the number of places to move the decimal. If the exponent is positive, you have to move the decimal to the right. If the exponent is negative, move the decimal to the left. So let's take a look at the following examples. We're asked to write 2.998 times 10 to the 8 meters per second in standard notation. So taking that number, when we look at the exponent next to 10, we see that it is a positive number, so we are going to move that decimal to the right. And the exponent itself tells us how many places to move that decimal. So in this case, we are going to move the decimal 8 spots. So we'll move it 1, 2, 3, 4, 5, 6, 7, 8. And behind that 8, we are going to fill in those places with zeros. So in this case, we'll have 2998 followed by 5 zeros. And we can imagine that the decimal place is there. We won't actually draw it in or write it in, but we'll imagine that it is there. And if we count the number of places now that we've moved that decimal, we would have seen that we've moved it 8 places. So we moved it 1, 2, 3, 4, 5, 6, 7, 8. And we now have a number in standard notation. In the next example, we're asked to write 1.5 times 10 to the negative 4 in standard notation. So similar to the previous example, we're going to take that number, 5 times 10 to the negative 4, and convert it into a number with zeros, in this case, in front of it. So in this number, the exponent, and the fact that it's negative, tells us that we'll have to move the decimal place to the left. And the number itself tells us that we'll have to move that decimal place 4 places. So we'll take our 1.5 and we'll move it 4 places to the left. So move it 1, 2, 3, 4, and those places now in front of the 1, we will fill it in with zeros. And in front of the decimal place, of course, we'll write a 0 as well. And we should have 3 zeros, and then our 1.5. And so now we've taken that number of 1.5 times 10 to the negative 4 and converted it into standard notation. At this point here, I would like you to pause the video and complete the scientific notation worksheet. Return to the video once you've completed those questions. All right, welcome back. Next part, we are going to talk about the metric system and how we convert between units within the metric system. So what is the metric system? Metric system is an agreed upon system of measurements used by most countries and scientific communities. Here in Canada, we use the metric system for our distances, for our masses, etc., etc. Now, within the metric system, base units are used and prefixes are added to change the base units. The following table shows common base units of measurements. So when we deal with length, for example, our base unit is going to be the meter. And the symbol given for that is a lowercase m. When we deal with mass, our base unit will actually not be the kilogram, it will actually be the gram. I don't know why that's there. And the symbol for that will actually just be a lowercase g. If we deal with time, for example, the base unit for time is the second, and the symbol for that is an s. And we have other base units as well, such as the ampere, the mole, which you deal with in chemistry, but we won't deal with those in grade 10. We'll deal with mainly mass and length and time. So within the metric system, the metric system itself is based on multiples of 10 going between each prefix. Each multiple of 10 has its own prefix, so a syllable that is joined to the beginning of a word. And the following table shows common metric prefixes. So here, right in the middle of the chart, we have our SI unit. This is what our base unit starts at. So for example, if we're measuring length, our base unit would be the meter. And so that would just be equal to 1. If we move up one prefix, we are increasing this by a factor of 10. And generally every time we move up, it's increasing by a factor of 10. If we move down, we are decreasing that base unit again by a factor of 10. And depending on the prefix that we use, it also indicates that factor difference between that unit and the base unit. So, big long conversion chart. How do we use it? How do we put it into play? Let's take a look at some following examples. So we use this chart ultimately to convert into units. It's not a chart you will have to memorize, it's a chart you will actually be given. So it is important to know how to move between the different units. So conversion from unit to another unit is actually relatively easy if you know the base unit and the meaning of the prefixes. So for example, if we have 1 kilometer, if we go back and look at our chart, so here is a kilo, and a kilo indicates 1,000 factor difference between the kilo and the base unit. So what that means is that, for example, 1 kilometer will be the same as 1,000 meters. In the other example, if we had 1 millimeter, and if we go back and have a look at the chart, here is our millimeter with that symbol of M. A millimeter is 1,000 times smaller than our base unit of the meter. So what that means is that 1 millimeter is 1,000th or 1/1000th of a meter, so it would be 0.001 meters. The other way that we could think about this as well is that if we have 1 meter, this is equal to 1,000 millimeters as well. So when you're converting from units, there are some steps to follow when you're converting. So you have to know when to multiply, when to divide, and what to multiply and divide by. So the following examples will help demonstrate how to convert between units. In the first example, we're asked to express 56 centimeters in meters. So the way to do that is we always take our number that we start with and we include the units in this because units are going to be important. And using our chart, if we identify where that centimeter is on our chart relative to meters, so again, here's our meter, the base unit. Our, sorry, that's decimeter. Our centimeter, below the decimeter, is 100 times smaller than our base unit. So we have 100 centimeters in 1 meter. When we're converting from one unit to another, what we do is we take the number that we start with and we're going to multiply it by the unit that we're interested in converting it to. So in this case, we want to convert it into meters, so we're going to multiply our number by 1 meter, and we're going to set it up as a ratio. So we're going to take our meter, divide it by the number of centimeters that go into 1 meter. So in 1 meter, we know that we have 100 centimeters. So we're going to take our 56 centimeters, multiply it by 1 meter, change anything, and we divide it by 100 centimeters. The nice thing about this method is that our units of centimeters will cancel out, and we will be left with units of meters. And so when we divide 56 by 100, we get 0.56 meters as our answer in meters. In the second example, we're asked to express 6 kilometers into meters. So once again, we take our number, in this case we have 6 kilometers, and we're being asked to convert that into meters. If we go back to our conversion chart, so we start with our units of meters here. Here are our kilometers. So for every 1 meter, or sorry, for every 1 kilometer, we are going to have 1,000 meters. And so if we convert that 6 kilometers into meters, we're going to multiply it by the units that we're interested in converting it to, and divide it by the units that we are starting in. So in this case, kilometers. So we know that for every 1 kilometer, we have 1,000 meters within that 1 kilometer. So when we convert our 6 kilometers into meters, we are going to multiply it by 1,000. And in this case, we get 6,000 meters as our answer. In the next example, we're asked to express 3,200 centimeters in kilometers. This one is an example of where we're going beyond the base unit. And if we go back to our conversion table, we identify where centimeters are, so our centimeters are here, our kilometers are here. So going between centimeters and kilometers is going to take a two-step conversion. First thing that we're going to do is take those centimeters and convert them into meters. And then we're going to take those meters and convert them into kilometers. Bit tricky, but the math will work out. So we start with our 3,200 centimeters. We are going to convert those into meters, and we're going to follow it the same way that we've done in the previous examples. So we're going to multiply that by the unit that we're interested in converting into, in this case meters, and we're going to divide by the units that we're starting with, in this case centimeters. So we know that for every 1 meter, we are going to have 100 centimeters. So we're going to take our number, divide it by 100. Right now, we have our units of centimeters canceling out, and right now we're in units of meters. We need to get to kilometers, so we need to do another conversion. So once again, we're going to multiply this again. We're going to multiply it by the unit that we're interested in converting to, which in this case is kilometers. We're going to divide what we are converting from, which in this case is meters. And then using our conversion chart again, we know that for every 1 kilometer, we have 1,000 meters. So we're going to take our 3,200, we're going to divide it by 100, and divide it by 1,000. When we do all that, we will get 0.032 kilometers as our answer. In the final example, we're asked to express 0.00583 seconds in milliseconds. And this is just an example of using something other than length when we're converting. So same as before, we start with our number, that 0.00583 seconds. If we were to go back to our chart, our second is our base unit. Our milliseconds we're going to have 1,000 milliseconds per 1 second. So it's a 1,000 factor difference between those two. So to convert into milliseconds, we are going to multiply by the units that we are interested in converting to. We're going to divide our number in the units that we are converting from, in this case, seconds. So we know that for every 1 second, we are going to have 1,000 milliseconds. So that when we multiply the 1,000 by our 0.00583 seconds, we get a total of 5.83 milliseconds. At this point, I'll ask you to pause the video here and complete the metric conversion worksheet. When you've completed that, please come back to the video and we will continue on with the next portion of the note. All right, welcome back. And in the last part of this note, we are going to talk about measurements and significant figures and where that fits in. So with any measurements, any observation from any experiment may be qualitative, so it's described using your senses, or quantitative, a measured quantity. When we deal with quantitative observations, this actually helps describe things such as how far away something is, how massive it is, or how much space it takes up. Quantitative observations generally require the use of accurate measurements. So when you take the mass of something, you need an accurate measurement if you're going to use that in your experiment. If you measure the volume of something, you got to make sure that it is accurate. With any device that you use to measure anything, no measuring device can give absolutely exact measurements. Quantitative data from any measuring device is going to be uncertain. You can describe this certainty in terms of precision and accuracy. And before we talk about precision and accuracy, looking at the example that we have on the board of those two rulers measuring this length of this object here, the ruler on the top, if you were to measure the length of that object, you would get it as 8 based on this ruler here, it would be 8.7 centimeters. Because we have these little dashes and markings on here, we can accurately get a more accurate measurement. Whereas the ruler on the bottom, both of these rulers measure centimeters, but the ruler on the bottom doesn't have those millimeter markings. So if we were to try and determine the length of that ruler, we couldn't get an accurate measurement. We would estimate it to be somewhere maybe 8.6, 8.7, maybe even 8.5, depending on how you read it. So we have uncertainty in terms of the numbers that we get from our measuring devices. And this can actually be determined, described in terms of precision and accuracy. So when we talk about precision, we talk about the exactness of a measuring device. So in terms of the rulers at the top, the ruler at the top, on top of the object, will give us a greater precision because of those millimeter markings on there compared to the ruler on the bottom. When we talk about accuracy, accuracy is how close a measurement or calculation comes to the true value. So basically, the more precise you can be, generally speaking, the more accurate your measurements are. So to improve accuracy, scientific measurements are often repeated and combined as an average. This is why you do multiple trials and combine them as an average. The more trials you do, the more likely you're accurate, the more likely your data is accurate. So the following diagrams now here describe the difference between accuracy and precision. Note in the first diagram, all the darts are close together. So we've hit a similar location on that dartboard. So we can say that the darts that we've thrown, the area that we've hit, are precise because they are very close together. But they're way off from that bullseye that we're trying to hit. So we can say that they are precise, but not accurate. So we can have, for example, equipment that will give us precise measurements, but it's not close to what that true value should be. In the next example, we have darts that are all over the board, and they're not anywhere close to that bullseye. So in this case, it's neither precise nor accurate. Our measurements are all over the place. We don't know what's going on here. And in the third example, you'll note that all of our darts are now in the center at that bullseye. So we have an exactness there, so we can say it's precise. And because they've all hit that target, hit that bullseye, we can also say that it is accurate. So ultimately, with all of our scientific measurements, we would like them to be precise and accurate. This will give us good data, repeatable data, and ultimately help prove or disprove our hypothesis. So the thing to note is that when you're making a measurement, any measurement, you're only making an estimate because there's actually uncertainty in that measurement. So how do we represent that uncertainty in the numbers that we write down? Well, this is where significant digits come into play. So significant digits are used to represent the amount of uncertainty in a measurement. The significant digits in a measured quantity include all certain digits, so the ones that you're certain about, and it also includes the first uncertain digit. So how do we determine if a number is significant or not? Well, we have a list of rules for determining if a number is significant. The first rule for determining a significant digit is that all non-zero digits, so numbers between 1 and 9, are considered significant. So from the first example, where we have the number 123 meters, all three of these numbers are greater than 0, so they're non-zero numbers. So we would count these as significant. So we would say this number has 3 significant digits. In the next example, again, all of our numbers are non-zero numbers, so we count them all as being significant. So in this case, the number 23.56 kilometers has a total of 4 significant digits. The second rule for determining significant digits is that zeros between non-zero digits, we count these as being significant. So in the following example, where we have 1,207 meters, because this 0 falls in between two non-zero numbers, this 0 is going to be counted as significant. So in this case, in this number, we have a total of 4 significant digits. In the next example, we have the measurement of 120.5 kilometers per hour. In this case, again, this 0 falls between two non-zero numbers, so this 0 is going to get counted as significant. So this particular measurement has, again, 4 significant figures. In the next rule for determining significant figures, any 0 that follows a non-zero digit, so it follows a non-zero digit, and, the key word here, and, is to the right of a decimal point, is counted as significant. So in the following example, we have 12.50 meters per second. The number of significant digits in this would be a total of 4 significant digits. So here we have a 0 that is following a non-zero number and is to the right of that decimal place. So in this case, this 0 counts as a significant digit. So we have a total of 1, 2, 3, 4 significant digits. In the next example of 60 kilometers, note that this 0 does not follow a, or it does follow, sorry, a non-zero number in that 6, but there is no decimal place. So in this case, this number would not be counted as significant. So that 0 would not count. We'd only count the 6 as being significant, and we'd only have 1 significant figure in that 60 kilometers. Note again that in the following example, we have 60.0 kilometers. So in this case, we do have two zeros here that do follow a non-zero number. Because we have a decimal place in here, both of these zeros are going to be counted as significant. So both of these guys will count. So when we count the number of significant digits in that number 60.0, we have a total of 3 significant digits. In that last example on this page, we have a measurement of 120 meters. Again, we have a zero that is following a non-zero number. We don't have a decimal place, so we don't count this zero as being significant. So in this case, we only have 2 significant figures. Now, rule number 4 for determining significant figures is that zeros used to indicate the position of the decimal are not significant. So in the following example of 0.00034 kilometers, when we're determining significant figures, note that these zeros here are to the right of that decimal place, but they are in front of those non-zero numbers. They are not following it at the end. So in this case, all these zeros would not be considered significant, so we would not count them. So in this case, it would just be the 3 and the 4 counted as significant figures, so we'd only have 2 significant digits in that number. In the next example, where we have 0.0350, again, the zeros in front of the number, although this 1 0 here is to the right of a decimal, but because it does not follow our non-zero numbers, those 2 zeros do not get counted as significant. The 0 at the end, because it is following our 3 and our 5, and it is to the right of our decimal place, does get counted as a significant figure. So in this case, we have a total of 3 significant digits. And lastly, any counting numbers, so anything that we actually count, has an infinite number of significant figures. So for example, if we were to count 6 apples, we know there is no uncertainty in that, so we would say it would have an infinite amount of significant figures. In the following example, if we have 125 people, we know we've counted 125 people because we can't have half of a person, so we can't have 125.5 people. We can't have 124.75 people. We know we have to have an exact number. So in this case, again, because it's an object that we have counted, it has an infinite number of significant figures. So those are our rules for counting significant figures. It is your job to make sure that you know those and how to determine whether a number is significant or not. Now, we use significant digits in mathematical operations also. In this case, we'll discuss how we handle significant digits when we're adding or subtracting, and how we determine how many significant digits we should have in our answer. So when we're adding or subtracting, you perform the operation as normal, and then you round off the answer to the value having the fewest decimal places. So what does that mean? Well, let's take a look at the following example. So we have our 2.3 centimeters plus 6.47 centimeters plus 13.689 centimeters. We add those numbers together as normal. We will get the number 22.459 centimeters. To determine the number of significant figures that we are supposed to have in our answer, we have to go back and look at the numbers that we used in our calculation and determine the number of decimal places in each number. So in this number here, the 13.689, we had 3 decimal places. In 6.47, we have 2 decimal places. And in 2.31, we only have 1 decimal place. So within our answer now, our answer has to have the same number of decimal places as the one with the fewest. So in this case, our answer should only have 1 decimal place. So we will round off the end of our answer to reflect that 1 decimal place. So in this case, we'll only carry 1, we have to round off, and in this case, we'll round up so that our final answer will be 22.5 centimeters. When we're multiplying and dividing significant digits, we perform the operation and then round off the answer to the least number of significant digits of the data value. So similar to the last example, we do the operation as normal, and then we go back and determine how many significant digits our answer should have. So in this case, we have 2.342 meters times 0.063 meters times 306 meters. When we multiply those all together, we get a really long answer, 5.149076 meters cubed. Now, all of those numbers are not significant. There's actually uncertainty in pretty much a lot of those numbers. So we only want the numbers that are going to be significant. So how do we determine how many numbers to carry? We have to go back and look at the numbers that we used in our calculation. So in going through each of the numbers, determining the number of significant figures, the 306 meters has a total of 3 significant figures. The 0.063 meters only has 2 significant figures. Our 2.342 meters has a total of 4 significant figures. So our answer should have the same number of significant figures as the number with the least amount of sig figs. So in this case, our answer should only have 2 significant figures in it. So we will have to round accordingly. So our answer, we'll have to keep the 4 and the 5. Those 2 are the significant figures that we'll have to take. The rest of these numbers we'll have to determine whether we round up or round down. In this case, we are going to round down, and we're just going to drop those numbers at the end. So our answer in this case is going to be 4.5 meters cubed. So that's it. The video is done. From here on in, just complete the significant digits worksheets. Just worksheet. And make sure that the other example questions are finished. Help each other out if you have any questions. This is new material that you guys are seeing and a lot of information that was thrown at you guys.